All right. So, what I have planned for today is just quickly review and talk about different methods of measurement. And by measurement, I'm specifically talking about how to measure those three specific elements that I said any system, in our case, any vibrating system has. Right? We said any vibrating system, any oscillating system has three specific elements. One is an element that stores kinetic energy, right? It's mass or inertia. Second is an element that stores kinetic potential energy, like spring or stiffness. And the last one would be the element that dissipates the energy. And in this case, the only one that we know for so far, or we have learned about, is viscous damping. So the topic would be measurements, but keep in mind that's what I mean by measurement, measuring those three quantities. Right? Because that's where that's what we need. Right? I'm talking to you about, well, that's how we study spring mass system, spring mass damper system, but now we need to know, well, how can I connect the real life systems into all these equations, system response, different ways of studying the system's behavior. So the first one would be, well, I guess I'm gonna phrase it this way, right? We need to know these three quantities or parameters to be able to model our system, right? You're taking a system from real life into your own space, environment, I would say engineering way of modeling a system. Right? We are studying how to model systems, but then we need to know, what parameters we can measure from the real system and use it for modeling. So I'll put it this way: for modeling purpose, let me put it a little. For modeling purpose, that is one of the purposes, we need to be able to measure the three elements of a given oscillating system. Those three elements, I'll just put it here like this before I get into each of them, would be mass or inertia, right? Spring or stiffness, I would say. Spring or stiffness or elasticity. We talked about in the previous class about how solid objects also can be looked at as a spring, right? And the last one is damping, that in this case so far we only know viscous damping. So quickly go over the first two. They're less complicated, obviously, at least to the extent that we care about in this course. Right? Mass is pretty straightforward. Mass, inertia. You know how to find the mass. We can just measure it. You can use a scale and find the weight and get the mass as long as you're on Earth. And you know the acceleration due to gravity G, you can find the mass. Pretty straightforward. Moment of inertia is a different story, right? So I don't get into details about that, but if you take a look at your textbook, I think in your textbook section, probably if you're interested to know more, take a look at your textbook on section, I believe it's 1.6. I'm going to double check that. But it has a lot of applications. Well, not a lot of applications. Specifically, it's used in aerospace industry. I've seen that they use this kind of special pendulums, right? It can be a torsional pendulum or as they call it, a platform pendulum. So in case of a torsional pendulum that I think is mentioned in your textbook, it's pretty much a I would say some kind of circular disc like this, and it's hanging by some thread, like some threads or 2 or 3 of them attached to this disc in different spots. So what they do is that they put the object they want to find its moment of inertia there. They want to find its moment of inertia. Now, in this case, a cube, I'm just putting as an object, but in those kind of industries, like specifically the aerospace industry, we're talking about very complicated parts, like a CNC machined. It's already, they have done some finishing, they did the surfaces, it's some a lot of time weird shaped parts. They want to find its moment of inertia, mass moment of inertia, because they want to do some modeling, some simulations maybe. What they do is that, well, as long as they know the length of this thread, and don't quote me on that, but I think they're pretty much the same length. What they do is that they give this plate a little bit of rotation, like some, I would say, small rotation, right? Some kind of, they turn it a little bit and let it go. So it starts oscillating in torsional direction. Right? It starts oscillating this way. A small rotational oscillation. And knowing the properties of this disk, which they already probably found, let's say I, mass moment of inertia for the disk, radius of the disk. Let me see if I have them on my notes to be more specific. You can always take a look at your books, your book, but I actually have it something here. So M naught, right? As long as they know the properties of this disk, you can actually find a mass moment of inertia. Right? They just say I is equal to, I have the equation there, but it's from the textbook. Don't be worried about how it's derived, right? M naught plus M divided by 4 pi squared L minus IO. Right? M being the mass of this object, right? We said mass we can measure. So they can find the mass moment of inertia of the object on this plate. It's actually, that's what they do experimentally. This is torsional pendulum. Right? They can also have, let me just put it here. So actually, torsional pendulum. They also can do it using a platform pendulum. It's a little different. The platform pendulum is pretty much just a plate like this. And then it's connected, if I consider this as the line, it's connected with wires or threads like this. And they put the object they want to measure its moment of inertia there. Now, in this case, you have the properties of this one. You have the properties represented with IP, MP, properties of this, M, O. Some other parameters. I don't get into details. You can take a look at this. This is not in textbook, but you can always probably find it. Platform pendulum. So I can put the name so you can look it up if you want and you're interested. These are more like experimental methods. Obviously, we're not gonna deal with these. I just want you to know that how that works. Right? So it pretty much swings this way as opposed to the other one that is torsional. This just swings around this whatever line or whatever axis that these two wires are connected and holding the platform, and measuring the time period for that. Right? They can find the or given the parameters, they can find the inertia of the object. These are 2 methods, at least I'm aware of. Might be more. Um, Again, we're not going to deal with this in our course. I just want you to know that how it works. And if you see it later on, especially in aerospace industry, you'll see doing these. If you end up in that sector, you'll see they do these, especially the rotational oscillation or torsional pendulum I've seen they use. So that's just about mass. It's good enough. You know, that's all you need to know. How can we measure this parameter for modeling? The second one would be the spring, or I put it as also stiffness. Now, I briefly talked about it when I was talking about the spring and I introduced the spring, right? If we have a spring, let's say attached, let me be more organized, let's put it here. I don't know where to put it, I'm a little lost. Let's just put it here. I have a spring. Now, if I start applying force to this spring and measure how much the spring is stretched for any given force, if I draw two axes here, F versus X, F being the force applied, X being the deformation in the spring. I start, every time I apply a specific force, like this much force, I get this much deformation. Then I apply this much force, I get this much deformation. This much force, I measure this much deformation. And if my spring is capable of compression, I compress, so the force is negative, I get this much deformation. Right? The length is reduced, is less than the original length. And the same story here. For every force, I get a corresponding deformation. So I put this together, I can just connect these dots and get a line. That line should go through this point, at least as close as possible. Now, this line, right, this is the relationship between F and X. F is equal to Kx. So this line, the slope of this line, the slope is K, the stiffness of the spring. This is what you do in the first part of your next project that I'm going to post today. I gave you a spring. The amount of mass is attached to the end of the spring is given for every frame. So for each frame, let's say you put your coordinate system using the video tracker to analyze the video. You put it all the way at this end, right, somewhere here. Let's say you take X in this direction. Then for any given weight, right, you have the value of weight, which is your force, in this case W, mg, and you measure how much is the deformation in the spring. So you can plot this F over X, and once you plot this F over X, you can find the slope of that line, which would be this K value for a spring. So it's a little bit of system identification. This process, all these processes, we can put them all under system identification. We have a system outside, and we have to morning and speaking problem. We have to identify its parameters. So it's the first part of your project. Just be aware of, it's a little bit of a hint what to do and where to start. Now, we also talked about objects, right? Solid materials. We are not just dealing with springs, right? If I have, let's say, in this case, let's say I have a bar. Right? You said we can replace this bar with a spring. Now, this case, how do we find the stiffness of that spring? Remember, we said, for instance, if it's longitudinal direction, I'm pulling it. I said K would be AE over L. Right? If you remember, I said K equivalent would be AE over L, A being the area of that bar or rod I'm pulling, L being the length. So how do we do this one? Well, hopefully you remember a little bit from solid mechanics and probably the lab you had. You were doing tensile test. at some point. Hopefully you can. Correct me if I'm wrong if you didn't do it. You were getting some, at least for well-behaved materials, you were getting something like this. We don't care about the rest of it. But in the first area, somewhere here, if you follow the Hooke's law, it's a linear relationship. Right? And based on that really linear relationship, right, you get E, the value of modulus of elasticity. You could find the slope of this line and find the modulus of elasticity, this being stress, this being strain. Well, if you find modulus of elasticity, you're good to go. You can measure the area of the bar, you can find the length, and you can pretty much find the equivalent system, right? The spring that you can use to model this system under vibration. If there is it is under vibration, or it's oscillating. There's another case. One more case would be, well, you have a cantilever beam in this way. Let's say you have a cantilever beam. Right? The force is applied here. Well, we talked about this too. We said, well, if a force is applied here, we know the deformation would be in this form, delta. So we can apply different amounts of force or a specific amount of force as long as it's not too much that make it nonlinear. Right? It's a small amount, so deformation is not that much. We can measure delta. So once you measure delta, right, this would be FL to 3 over, I think 3EI, we said. And from there, you can find E again. You can measure I. I was the area moment of inertia. So you know the area, you can measure it. You know the force applying, you know the length of the beam. So you can find, as long as you can measure the displacement, you can find E, modulus of elasticity. So now you know your system. Now you can actually find the spring equivalent, right? For a cantilever beam. We introduced a K equivalent for cantilever beam. So you can just use that. I think it was 3EI over L to 3. So as long as you know E, you're good to go. Now you can even do dynamic testing. This is a static testing, right? You apply a force, measure how much it deflects. Right? Let me put it like static testing. You can do dynamic testing. What do I mean by dynamic testing? Well, give it some initial velocity or initial position and let it go, and it starts oscillating, right? Your cantilever beam, it starts oscillating. I have a ruler here, right? If I have a cantilever beam, I give it some initial displacement, it starts oscillating, right? As long as I can measure the time period for this oscillation, right, I can actually get, as long as the damping value is very low, which is a very big assumption to make. But theoretically speaking, you can measure the time period, the time it takes for this beam to go through one cycle, goes up, comes back where it was. If you measure that time period, right, from there you can actually find natural frequency. Or look, you can put it this way. You measure the time period, right, and you know the stiffness equivalent for a cantilever beam is 3EI over L to 3. So if I plug everything back, right, omega n being square root of K over M, I have K here, plug it in, everything together will give me square root of, this goes up, M, L to 3, divided by, this goes down, 3EI. So once you measure time period, well, you know the mass, you know the I, which is the area moment of inertia, you can measure it and calculate that depending on the shape of the cross section for this beam. And from there, you can again find your modulus of elasticity. Once you know modulus of elasticity, you can find your K equivalent. And then you have your system parameter you were looking for, which is a stiffness. So this is dynamic testing, I would say. Because obviously the beam is moving. So these are two different ways of finding the stiffness for a cantilever beam. when you want to model the motion of the tip of the beam. So you see, these are different ways, depending on what you're dealing with. If you have a spring, if you have a bar under tension, under pulling, or under compression or tension, or you have a cantilever beam. Same story is for if you have a clamp beam or simply supported beam. You can still use the same methods to find system parameters. You can find modulus of elasticity, measure other parameters like I and A, area, depending on if it's under tension or transverse oscillation, and use that to find stiffness. So 2 parameters so far. I told you how can you measure. Right? So how can you identify for a given system? You're an engineer. They give you a system. They tell you, well, give me a model that behaves as close as possible to this real system under these specific conditions. That's what you're going to do probably in a lot of places you're going to work as a designer. That's actually an art, to be able to develop models that they behave very close to the real system. So to do that, you have to get input from your real systems. How to do that? Well, mass and inertia, I told you how to do that. Spring is stiffness, depending on if you just have a spring or you have a solid system, you want to identify its parameters. That's what you do. And these are not new things. You already know the knowledge from before. You know stress strain curve, and you know Hooke's law. You know how to measure time period from what we talked from before. Now, the last one, which is the more tricky one, I would say, is the damping. Let's put it under damping. And in this case, I'm just talking about viscous damping. So any questions so far, folks? Did you follow what I'm saying, hopefully? Again, keep in mind, you take these courses, later on, you go and start your career. These are good. These are insights you need to have. You know, someone tells you, so what? You can model a spring mass damper, a spring mass system. That doesn't really help me with this beam I have or this specific situation I have. You can actually use whatever you learn, as long as you follow the correct procedure and you make the right assumptions, right? And always take into account and clarify what assumptions you have made. That's all you need to do. All right, for viscous damping, right, obviously this is also a dynamic kind of testing, right? We need to do a dynamic testing, and in this case, dynamic testing, for instance, if you have, let's go more general, if you have a beam, let's say I have the same beam, I want to measure its damping. There is this approach called model analysis, or experimental model analysis, as they call. What we do is, or vibration testing even, as more general. They typically put a sensor at the tip of this beam. It's smaller than this. This is too big, obviously. To measure the way it oscillates, right? I'm going to connect it to, let's say, some kind of screen. Now, what they do is that they hit this beam with a hammer. This is my way of plotting a hammer. So when you hit it, right, you give it some initial velocity or displacement, it starts oscillating, right? And you record that oscillation. It has a damping, so you get something similar to this. Now, knowing that recorded oscillation, you want to find the damping. Right? We know nothing else about this system. All we know, we don't know the mass, we don't know stiffness, we know nothing about it. We only have this recorded plot. Technically speaking, this recording in reality is acceleration, right? Because we use accelerometers to make measurements. But from acceleration, we can go to displacement, right? And whatever I actually tell you, it applies to velocity and acceleration, because it's going to end up being a relationship between two peaks. You'll see. Now let's see what we do there. Let me bring my more clear plot. I have it there. Move things around a little bit. I can't see. There we go. This is good. Put it here. Let's say this is what I measured. This is the outcome of that measurement. I want to use this to find viscous damping. Here, that's how here is how I go about this. I go one of these peaks and measure what the value of, let me first put the axes. This is xt, it's displacement in this case, and this is time, second. Displacement can be meter, millimeter, depending on what unit you have. So I can find what is the magnitude of at this peak. Right? I have a plot with some points measured. And I can find what is the magnitude of this peak. And I know what time it occurred. So let's say T1, T2. And this one, I call it X1, I call this X2. Now remember, back then when we talked about this system, we said if you connect these two peaks, remember that plot I plot for viscous damping? I said if you connect these peaks all the way, this curve, the equation for this curve would be A e to minus zeta omega n t. Now, because these points are on that curve, so obviously x1 would be A e to minus zeta omega n t1, the time that x1 happened. And x2 would be A e to minus zeta omega n t2, the time that x2 happened. Now, well, from first peak to second peak, well, the time is, if I want to write the relationship between these two t's, right, I can say t2 is nothing but t1 plus t, time period, right? Because I'm going from the first one peak to another peak. It takes one period to go from one peak to another peak. System goes and comes back to where it was as close as possible. So I know the relationship between T1 and T2, so I can rewrite these two. X1 would be A e to minus zeta omega n T1, and X2 would be A e to minus zeta omega n T1 plus TD. Now, I have to do a little bit of manipulation to get to what I want. What I'm looking for, keep in mind, I want to find damping. So I'm aiming for damping ratio first, zeta. I want to get zeta out of this and find a way to calculate zeta. So I want to kind of get rid of A, get rid of other things, and be able to take zeta out. But to do that, I'm going to divide the top one by the bottom one. All right, I can do a bit of X. X1 over X2. If you do that, A values are going to be canceled. So what you get is minus zeta omega n T1 divided by, and I'm going to expand the one at the bottom, like X2, well, A is canceled. I'll expand the T1 plus TD, so this becomes e to minus zeta omega n T1, right, times, remember, when we multiply two values, whatever we have as they're raised to, they add up. So this becomes e to minus zeta omega n TD. A lot of math you learned from before, they're coming back to your life. You thought you were done with them, huh? So once I write it this way, you probably can see that I can cancel these two. They're the same, and this is multiplication between them, so in the denominator. So I'll end up having pretty much just x1 over x2 being, I can bring the one in the denominator up, this negative becomes positive omega n TD. I want to get rid of this E, so I'm going to take an ln from both sides. So this becomes ln x1 over x2 is equal to zeta omega n TD. Put it here, TD. This is as close as I could get so far. Now, I have some information from before that I can use, right? I know that, let me just plug it here, identify it. That's where I am. I know from before that, let me write it this way. We know that omega or TD, let's start from there. TD is equal to 2 pi over omega d. And following that, well, obviously omega d would be, you should know that now, that hopefully you studied for the quiz, is omega n square root of 1 minus zeta squared. So what I'm going to do, right, is TD. Do it this way. What I'm going to do is that I'm going to take this TD, put it back in what I got. Keep in mind, I'm trying to write everything as a function of zeta, right? Because I want a relationship between damping ratio, I'm looking for damping, and only values I can measure from the plot, which are T1, T2, X1, and X2, right? I know nothing else about this system. So I'm going to plug back this TD into the equation. If you do that, let me go to the next page. I plug it back. I'm going to have an omega n on the numerator, another omega n in the denominator. They can be canceled out. Let me write it back again here. So this becomes ln x1 over x2. This becomes, I think, 2 zeta. I had omega n. Now pi comes here. Right, let me double check what I had there. I'm plugging in 2 pi, so 2 pi zeta omega n. And then in the denominator, you'll get omega n square root of 1 minus zeta squared. So I get rid of omega n's. So now I'm in a pretty good shape. It's going to be ln x1 over x2 equal to 2 pi zeta over square root of 1 minus zeta squared. Great. Now I have a relationship or an equation that describes the relationship between zeta, damping ratio, and x1 and x2. So if I have given the plot of that system, oscillating system, just by measuring the values of the peaks, I can find a damping ratio. Right? So let's just go about this for two specific cases. That's how they usually do it. When you have, there is this assumption to make your life a little easier. When you have very small damping, like when zeta is very small, as a result, zeta squared is going to be small. Right? So let me put it this way. For very small damping ratio, let's put it this way. Damping ratio, what happens is zeta is small. So zeta squared is very small. I put it this way. It's very much smaller than 1. So the denominator on the right side, square root of 1 minus zeta squared, I can pretty much say, well, that is just square root of 1. I can say zeta squared is almost equal to 0. Now, I'm going to define this as this whole thing on this side as delta. Don't confuse this delta with the delta I was showing to represent the deflection of the beam. Like, this is just a delta. Delta, I'm going to rewrite it here, defined delta as ln x1 over x2. This process is called logarithmic decrement. What happens? As you can see, why? We have a logarithm here, and the amplitude is decreasing. So the process, or this way of measuring this, what happens in this system is called logarithmic decrement. You will see it under that title if you look up different textbooks or different sources. So if zeta is very small, what happens is that, well, I can easily say delta, which is now defined as ln x1 over x2, as 2 zeta pi. That's pretty much it. So from there I can find zeta, right? Delta over 2 pi. That's all I was trying to find. From the beginning, all this mess I made, and the process, mathematics, I simplified things, multiplied things, divided things, just because I wanted to find a way to connect zeta, or damping ratio, which represent the damping for my system, to delta. Delta being the sum relationship, or ln of the ratio between two successive peaks. So this is the case for very small values of damping ratio. Keep in mind. So how small is that? Very good question. Unless I tell you that it's very small, do not use this. It's more practical that in practice, you have a very small damping, you can use this equation to make your life easier. But nowadays with calculators and computers, might not be that much practical, I guess. Now for large damping ratio, or large damping, you can't make this assumption anymore. So what you got to do is that you actually have to go there, this equation here, right? This one, and take zeta out. So I don't go into details, but you squared both sides, you get that zeta squared out of square root, and you're going to end up having in a squared, zeta squared, or second order or quadratic equation for zeta, and from there you can find zeta. Zeta can be negative. From there you can actually calculate zeta. So what I write here is coming from that equation, but I try to write zeta as a function of the rest of it. Right now is delta is equal to something. I take zeta out, and I want to write zeta as a function of delta. So that would become, or that becomes, square root of 4 pi squared plus delta squared. I can do better. Delta, this looks like 8. Delta squared. Now this is the relationship that you use more than 90% of the time. Given a plot, if you can find x1 and x2, or two successive peaks, find the relationship or the fraction x1 over x2, find ln of that value, that would be your delta. Put the delta there, it gives you your damping ratio. As easy as that. Now there is a special case, let me categorize things here, that what if we do not have two, so here I had two successive peaks, right? I had one peak here, another peak there. What if I had this peak and this peak? I had x1 and x3. I had x1 and x4. Maybe, what if I had peaks that were not successive? I'm not given the plot completely. I'm just given these values. How do I deal with that? So this is for, let me put it this way. Green probably is not the best color to use. For two successive peaks. If the peaks are not successive, you can pretty much follow the same process. What happens is that for, I would say for peaks and multiples of periods, right? Look at it, how many periods they are apart. What changes is that delta, the only thing that changes, right? The relationship, maybe I shouldn't have put it here. Okay, let me fix it. I don't want to write the whole relationship. The relationship is this for all the cases. Now, for peaks and n multiples of periods, delta is defined in a different way. Instead of being ln x1 over x2, now you have 1 over n being n multiples of periods, ln x1 over x1 plus nt. So if you have x1 over x3, right, this n becomes 2. So let me write it. So this is for peaks n multiples of periods, and for peaks, for successive peaks, keep both of them here. For successive peaks, delta is just ln x1 over x2. Just put it somewhere that you remember. I'm going to make square there, around rectangle around here. So this is the relationship you need to know, right? Delta in that relationship depends on what peaks you're looking at. Are these two successive peaks, or these are the peaks that are n multiples of periods away from each other? You can still use the value of x or the values of peaks. You just have to multiply that with that ln with 1 over n to make sure that the delta you put in that relationship that you want to find the damping ratio is correct. I can actually prove that this way by selecting two separate peaks, but at this point, I feel like all of you are probably moving your head. It's like, no way, I don't want to go through that. To save you from that process, I'll just give you what it is. I don't even think that the book did that. Maybe it did. I have to double check. All right, that's it. So now you can do system identifications. You can, if you are in a situation, you're given a system that you want to find an equivalent, a simplified equivalent of a spring mass damper system for that system, right? Or model for that system. You know how to find mass or moment of inertia. You know how to find stiffness for some simple cases and springs, linear springs. And you know how to find damping, in this case, damping ratio. Keep in mind, once you have damping ratio and you know mass and stiffness, you can find damping, right? Zeta is equal to C over C critical. C critical is 2m omega n. Omega n is just a function of mass and stiffness. So you can find omega n once you know mass and stiffness. You can find C critical. Once you know C critical and damping ratio zeta, you can find damping. Let's look at an example. This is pretty much the result of a test. Let's say, at least what the problem says, we have an underdamped shock absorber, and we want to design that. Let me just put the whole problem statement. An underdamped shock absorber is to be designed for a motorcycle of mass 200 kilograms. So we know the mass. When the shock absorber is subjected to an initial vertical velocity due to a road bump. Actually, I have a very interesting video of how the shock absorbers and dampers can affect the ride comfort. I'll share it with you on the forum later on, I guess today. I highly encourage you to watch it. That's pretty interesting. It's an old, I think it's from 1930 or 40, Ford company. They did some testing, and it's a very nice video illustrating the effect. The resulting displacement time curve is to be is shown, I guess. So we are phrasing it, is shown. And I'm just going to use the same plot I used. It's just for this purpose of illustration. So I can just use it, and it doesn't have any numbers on it. So it makes it a little easier to use it wherever I want. And that's a displacement, right? This is xt, and this is time t. What we're asked to do is to find the stiffness and damping. Damping constant of the absorber. What we are given, the information we are given based on this plot is that we know the time between these two peaks is 2 seconds. And if we consider this x1 and we consider that, so we're given two consecutive peaks. This is x2. We know that x2 is equal to x1 over 16. These are the informations given. These are the information given. And the shock absorber, I'm going to do my best to remake it at least to some degree. It's pretty ugly shock absorber. But by that, they're trying to say we have a damping there, we have springs here, and then from there, it's connected to some that's a very ugly. But you get the idea, I guess. To make it a little more obvious, that's motorcycle, I can do this. Right? And these are like, this is K over 2. So the whole thing is just K, and this is the damper. Let's see. Some bump on the road, and as a result, we get this measurement. All right, let's use what we learned. All right, where do I start? I'll start with delta. I guess I'll just go a little faster over this example. Stop me if something doesn't make sense. I usually ask you to tell me what's going on, but I just want to go a little faster so we have a few minutes before the quiz so you guys can get into the mindset. So I start from delta. I have two successive peaks. Delta would be ln x1 over x2. That would be ln, well, x1 over x2, well, I'm given, right? This pretty much gives me x1 over x2. That would be 16. So this becomes 16. I don't have x1 and x2 values, but I know the ratio. So this becomes 2.773. Is it? Yeah. Well, now I have delta. Right, pretty much use the relationship or equation I introduced. Zeta is equal to delta over a square root of 4 pi squared plus delta squared. So this becomes delta over square root, if I forget, 4 pi squared plus delta squared. If you do this math, right, just plug in delta pretty much, not that much complicated process. It'll give you 0.40. Don't know why my handwriting gets worse. 4037. No unit, it's a ratio. No, that's the tricky part. So far, so good, right? Now there is another piece of information I can use here. The next step would be I have to find the stiffness and damping constants. Right? These are what I'm looking for: stiffness and damping constants. constant. I don't know why it says constant. I have to find that, those two. So to do that, I'm going to use another piece of information I'm given. I'm given the value of time period too. So I can use that to find the natural frequency. Once I know the natural frequency, I can find critical damping. Once I know critical damping, zeta is nothing but C over C critical, so I can find C. And knowing natural frequency, I can also find the stiffness because I know the mass. It's 200 kilograms. So that's what I do. TD would be 2 pi over omega D. Would be 2 pi over omega n square root of 1 minus zeta squared. So from there, I can find omega n, which becomes 2 pi. Moving things around, it's going to be TD square root of 1 minus zeta squared. Now I know zeta, I know TD, I'm given TD. So I can find, I can easily calculate natural frequency. That becomes 3.434 rad per second. Immediately once I get natural frequency, I know natural frequency is the square root of K over M. Right? It's not damped natural frequency, it's natural frequency. So it only depends on the stiffness and mass. So I can find the stiffness, M omega N squared. I know M is 200 kilogram, natural frequency I found already. So the value for K, if you do this math, if I did it correctly, double check the numbers always whenever I give an example. I highly encourage you to double check the numbers. This becomes the value of stiffness. Once I'm done with this, let's go to damping constant. As I said, damping constant is C over C critical, right? Damping ratio, sorry. Zeta, we all know these from before. And C is 2M omega N. So what happens is, well, pretty much I can just find the damping constant by putting it as 2 zeta M omega N. That would be 2, I forgot what the value for zeta was, 0.4037. 0.4037. I know the value for mass is 200 kilograms. I'm given omega n. I calculated that. It was 3.434. 434. Right? So do this math, you will get the value for damping constant. I got, hopefully I'm correct, 554.5 Newton second per meter. All these are based on the fact that the X is calculated as a meter. So let me put it, add it here. Sorry, going back and forth between the slides. I know it can be annoying. This is the unit meter for this. So again, just to recap, right? I got the measurement. I knew how the system responded to this bump. I knew the mass. From that measurement, I wasn't given exactly the values of x1 and x2 for 2 successive peaks, but I was given the ratio between them, which is good enough for me. I could find delta. From delta, I could find zeta, as we learned today. And from what we know from before, I was given the time period for damped system, so I could find natural frequency from there. Once I knew natural frequency, given the value of the mass, I could find the stiffness. Knowing the stiffness, knowing the natural frequency and the mass and the damping ratio, I know damping ratio C over 2M omega N. 2M omega N being the value of C critical damping. From there, I could find the damping constant. Hopefully, it made sense. I'm just going to stop here. Just one point. Important point, guys. I only talked about displacement response. If this was velocity, instead of x, if we had here, I'm going to delete it later on, but just want to put it here. If I had x dot, If I had x double dot t, velocity, acceleration, did not matter. I could still use the values of the peaks. Can someone tell me why?
Is there no, is the only way you find x1 and x2?
Yes. Hopefully you're pointing at the same thing that I'm trying to say. Anton, it was you, right? Or
No, it's Joseph.
oh, yes. Sorry. I'm still getting to know the voices. So because x1, because all I care about is x1 over x2, and x1 over x2 is doesn't matter, you know. It doesn't have a unit. Can be the ratio between velocities, can be the ratio between accelerations, can be the ratio between displacement. Doesn't matter. I can always use the ratio to find delta. That's all that matters. So this x could be velocity or acceleration, still the same holds true. Okay, I'm just going to stop.